Okay, let's first recap what we learned last time. We are still talking about angle modulation and phase modulation and frequency modulation, right? And this slide shows you some definition of angle modulation. So since we discussed multiple times, let's move ahead. And as you know, we have a PM and FM, and we look at this PM, meaning the phase modulation and also the frequency modulation multiple times, right? So now you should be familiar with this notation. So message go into the phase part. So now the angle, always angle has a 2 pi fc plus phase, but message go into the phase. So the angle is simply written like this. Whereas in FM, your message goes to the frequency. So therefore, your frequency has your message. So therefore, this is a carrier frequency and plus message. And message is part of the frequency. So therefore, the output frequency is now fc plus some other things. So your frequency is now drifted. Your frequency is now changed, right? So putting this frequency into the angle, now you will see an integration, right? Because frequency and angle has that kind of relationship, right? Angle, frequency goes into the angle, and then you can rewrite it, then you can see the integration of a message. Okay? So therefore, put this angle into your original angle in the carrier. Now you'll see this one as a frequency modulation. So you want to remember this one, right? Message is part of the phase, and message is part of the frequency, but when you put this one out, then you'll see an integration. Okay? So that's a frequency modulation. And this one is a visualization. Let me just skip that. We talked about narrowband FM last time, right? Okay? So always we start from a simple message, and this is our message, simple example. And our message is just a single tone. You know tone, right? Tone means frequency. So this one we call that a single tone message because this message has a single frequency, single tone message. That's what we called. Okay, see here, single tone message, right? So using this single tone message as an example, we put this message into the frequency because we want to do FM, right? So put this one into the message here in the frequency. So therefore now the output frequency Fi is a carrier frequency Fc plus Kf, some constant value, and Mt, right? That's Mt. But our Mt is this single tone message with a certain amplitude. So put these two constant value. This is the amplitude of your message. This is some constant value. Put this together, we want to make it as a delta F. So what is the delta F? So delta F is the maximum frequency deviation. Okay? So Fc is the carrier frequency, okay? And then your frequency can be changed by this much. Frequency is changing within this range. So how much deviation, how much change you see in the frequency, that's delta F. Because you see a cosine always has a maximum value 1 or minus 1, minimum value minus 1. So the output frequency after you do the FM modulation, Fc plus delta F or Fc minus delta F. So that's the range. Okay, the frequency is changing from minus delta F to the Fc plus delta F. So that's the range that you see the frequency is deviating. So that's the maximum frequency deviation, right? So we see that delta F is like this. So this is a frequency. So put this frequency into the angle. Now we want to get this angle here. Then as we discussed earlier, when you put this frequency into the angle, now you'll see the integration of the message. So our message is cosine. So when you do the integration of the cosine, now you get a sine. And in addition to that, when you do this integration with respect to t, now the 2 pi fm is a constant value coefficient. So put this coefficient out, right? Because you do integration. So 2 pi, and here the 2 pi cancels out, and fm goes here. So you will see these things. Okay, when you do the integration of this, and here put it here, now you will see this one, right? Cosine becomes sine, and fm goes down here. So you'll see this coefficient Again, this is a coefficient, some value. So delta F divided by Fm, and we call this one as a modulation index. Okay, modulation index. So definition of modulation index is this one. Beta is delta F divided by Fm. If we consider the narrowband FM, what that means is the the modulation index beta is a small value, right? So if the beta is small, this is a very special case. Okay? In this special case, beta is small. Then in this equation right here, we always start from this one. If the your message is single tone message, okay, your message is single tone. Let's go back. If your message is single tone like this, right, then eventually you put this one into frequency, and frequency go to the angle, and once you get the angle, put this angle into the carrier, then eventually you get this one, right? So this is the signal you are transmitting over the air. ST is the transmitting over the air, right, for that single tone message. So this is FM signal after you do the FM modulation from the single tone message. So this is eventually what we are what we're transmitting over the air. But now what we want to look at is, what does signal look like? That's what we are trying to see. And in order to see that, we use identity, trigonometry identity, to change this one into the second equation, right? So this is a cosine A plus B. So it's like cosine A, cosine B, minus sine A, sine B. Okay? Like this, right? So using simple identity, we just change from here to there. Okay? So these two are same thing. And now if we assume that beta is small, then using these two approximation, cosine beta something, and beta is small, then it can be approximate to 1. And sine beta something is this inside parameter goes out, right? So it's like a sine x equal to approximated to x, okay, something like that. So using these two approximation, now this second equation can be approximated or can be changed into this one. Okay, once you use this approximation, this one now changed to this. Okay, so it becomes more simpler now, right? It becomes simpler. Okay. When I look at this one again, go to next slide. That's this one. We can again rewrite this one into this way using another identity. Okay, so that's this one. Sine A sine B equals to cosine A minus B minus cosine A plus B. This is another identity. So using this identity, we again change this to this. Once you do that, now you'll see three different terms. Cosine term, this is a pure carrier, just carrier component, right? We have a one carrier component, and we have a two more frequency, but this frequency is FC plus FM. This is FC minus FM. So when you look at this one, now you'll see that three different frequency components. This one is a frequency FC. This is a frequency FC plus FM. This is a frequency FC minus FM. We have three different frequencies, right? Three different impulse. That's what we see. So this is only for the narrowband FM. Okay? So that's the case. And also remember that this one looks almost similar to our previous amplitude, traditional amplitude modulation, right? It looks very similar. The only difference is that you have a different sign here. So that's another thing that you can notice. Okay, but we are more interested in wideband FM because narrowband FM is not really used much. So we are more interested in wideband FM. So what we are trying to do is we are going back to the original ST. What was the original ST? This is the original ST. Okay, so this ST was the signal we transmit over the air in case of this message. So this one was our message, single tone message. Using this message, we want to do the FM modulation. Once you do the FM modulation for this message, you're gonna get this, right? So this is the original, the signal we transmit over there. So we always start from here. But you know, this is also cosine, just cosine something. So therefore, what we want to do is we want to write it as real component of exponential, because real component of exponential j is cosine, right? So that cosine st is the same as this one. This one, we typically introduce this exponential of j because we want to call this one as a complex exponent, complex envelope. So when you introduce an exponential and minus exponential j something, it is complex, right? Because exponential of j is a cosine plus j sine, right? Cosine, right? Look, think about Euler equation. Exponential jx is a cosine x plus j sine x. So it is a complex value. So this is a complex actually. But you put the real, therefore we are going to only take the real component. It is a complex, but take a real component. So in that case, it's going to be same as a cosine, the previous cosine. So we just rewrite it this one, the originally cosine, but we write it here like that. And once you do that, it is exponential, and exponential of something plus some other thing. So therefore, we can rewrite this one as a multiplication of two exponentials, right? And then, since we have a multiplication of two exponential equations, so second exponential equations, we want to put it onto the front because this one is a function of fn. The first one is a function of fc. This is carrier component. So carrier component goes here, and ac times exponential of this part, exponential j beta sine. This one, we put it all together as s hat, s tilde. And we call that as a complex envelope. Complex envelope. Okay. Why do we call it as an envelope? Because think about the AM case, right? In the previous traditional AM, think about AM, amplitude modulation. In amplitude modulation, what you did was that you have some message, and you multiply the carrier, right? Then your message goes like this, and once you multiply the carrier, it goes like this, right? And your amplitude or envelope still looks like a message. So when you look at here, this is our transmitted signal. This is our ST. But when you separate carrier with some other things, that's what we do here, right? Here, inside the exponential, some part is carrier, some other part is message. So now we separate that. So this is a pure carrier part, and this is just a message part. Okay, just carrier and message. Once you do that, now this one, we can call that as envelope, right? Think about that way. A plus JB, right? Think about A plus JB. Think about phasor notation. A plus JB, just complex value, right? But you can rewrite as a amplitude and also phase. You can write it that way, right? A plus JB, that's just a normal complex form, but we can also use it as a phasor. This one looks almost same as a phasor notation. So this one is a carrier. It's like an angle, like a phase. And also this one looks like an envelope or amplitude, right? Because this one now is a complex value. Look at only inside the real. Inside here, we have complex value. Exponential is complex. And inside this complex, we basically separate that as a carrier and amplitude, and the carrier and the message part. And this message part looks like an envelope, and the second part looks like a carrier. So we call that as a complex envelope, like this. So our intention is to separate with the carrier and message. So that's what we want to do. Once you do that, now we have S hat T like this, just a pure message part. But now the problem is, this is our message. This is our signal. This is our signal looks like, but we don't know what this looks like. This equation looks complex, right? Exponential to the power j beta sine. So this one is a message, but we don't know what it looks like. So in order to see what this looks like, what we want to do is we want to take the Fourier series into here, like this way. We are basically doing transform to see this, okay, to see what we have. And you do it this way in Fourier series. But what is important here is this one, Cn. That's a Fourier coefficient. So eventually go here. We found out that Cn, the frequency coefficient, the Fourier coefficient, is same as a Bessel function. Okay, so simply speaking, this is our output. So St, the previous S hat t, equals to Bessel function times some frequency component and summation of n from infinite, minus infinite to positive infinite. So that's the another representation of our complex envelope. The previous S hat t was this one, right? This one. This is our previous hat t. So we want to see what this looks like. But using this Fourier series technique, we just change this into this. Basically the same thing, right? But once you change this into this way, now we can see it. Now we know what this looks like. Previous equation we don't know, but this equation we see what it looks like. And when you see this, what you can find out is this is a Bessel function, but when n is constant, beta is typically constant. Okay, beta is constant, and n is changing from minus infinite to infinite. But if you think about only one term, n, let's say, is a 0. In that case, you put n here also becomes 0, right? So exponential 0 equal to 1. And you have a sum value because beta is constant and it's also 0. So it's a J0 some beta value. In that case, we know that this is the Bessel function when n equal to 0. So if the beta, depending on what beta you have, x-axis is a beta. So for example, the beta is 1, for example, then here, right? So you can simply read this value. Maybe it's like a 0.7, something like that. So this one becomes 0.7, and this one becomes 1. So that's one component. And that's the DC component, because our frequency was 0. Now the n equal to 1, that means put 1 here, then we know that we have a Fm, that's the frequency, and 1 goes in here, so J1, and beta was also 1. So go back to the Bessel function. Now we are going to use this equation, this Bessel function, because that's the n equal to 1. And we simply read the beta equal to 1, then it's somewhere here. So it's about like 0.5, something like that. So it's like a 0.5 times exponential minus exponential j2 pi fmt, because n was 1. So that means our amplitude is 0.5 in the frequency component of fm. Okay? So think about, we keep doing the same thing again and again with a different n value. Right? So each frequency, now you have, this is the amplitude for each component, each frequency component with a different n. So that's what we see from this equation. Okay. So put this one, S hat t, back to this, because we originally started from here, right? We started from here. Okay, we start from here, and we know that S hat t was this one, but using Fourier series, we write this one into another way, right? Like a sigma and Bessel function. So sigma Bessel function equation, put that back here. Because this one was a equation we originally started. So then we get this. Put this one S hat t back to that, then we're going to get this one. Okay? We're going to get this. Now then, this is going to be, this is constant anyway. Bessel function is again constant. Real of exponential. So real component of exponential is going to be cosine. So again, we change it back to the cosine. We've done everything. Originally, we started from cosine, right? We originally started from cosine and change it to real component of exponential and do this, all the Fourier series and all these things. And now going back to the cosine. So this is our ST. This is our signal we transmit over there in time domain. Now Fourier transform to go to the frequency domain, now we see that this is our signal we transmit over there in terms of frequency domain. Okay? You see that we have a two direct delta function, right? And the frequency of that is Fc plus plus FM, NFM, and this is a Fc minus NFM, plus, yeah, this is a minus, right? So that's the signal we have. So therefore, we're going to see that what it looks like in the frequency domain in the next slide. But what we can see from that equation is that, as you can see here, the spectrum of FM wave, FM signal, when you look at the frequency domain, spectrum means frequency domain, right? When you look at this FM signal in frequency domain, now that signal contains a carrier component. What is a carrier component? Like Fc, frequency Fc component. A carrier component and also an infinite set of side frequencies. What does that mean is you have a lot of frequency component, but the carrier component is the frequency component with the Fc frequency. And you also have Fc plus FM, Fc minus FM, Fc plus 2FM, minus 2FM, Fc plus 3FM, minus 3FM, and infinite, right? So that's what they mean. All of that is a side frequency. So carrier frequency, carrier component is Fc. All the other things is a side frequency. But you have an infinite number. That's what we can see from that equation. So we can see it, right? We can go back here. When you look at this, that's what they mean. When n equal to 0, you're going to get 0. But when you put this one as hat t into here, as I said, this is the original equation. This is the signal we transmit over there in time domain. So when you look at here, right? Let's say n equal to 0. Then we only see the carrier component. Okay, but the n is infinite from minus infinite to infinite. So when n equal to 1, then we see Fc plus and FM, 2 Fc plus 2 FM. So we have infinite side frequencies. When you look at here, we can see that. Right? So that's the first observation. And second observation is, let's say when beta is small, that was a narrowband FM case, right? Only J0 and J1 have significant value. So that's what we looked at in the narrowband FM case, right? Narrowband FM, as we see, we only have a three frequency component, Fc and Fc plus FM, Fc minus FM. We only 3 in narrowband, right? That's what we're talking about here. What we talk about here is, let's take a look at the last one here. What that means is the average power of FM wave when you transmit ST, okay, you can always calculate the average power of the signal you transmit. So when you take a look at the average power, let's go back here. When you take a look at the average power of this signal, this is a signal you transmit, right? So let's take a look at the average power. How do you get the average power? Let's say in general, let's say there's ST. You're transmitting ST. You want to calculate the average power of ST. Then how do you calculate it? Simply square and integrate. So let's do that. When you do the integrate, how do you get? What do you get? Let's say your signal ST is a cosine. I mean, forget this. Just cosine. Simple cosine. What is the average power? Huh? What is the average power of cosine? Think about it. How do you get it? So average power is doing integration of square. So you're going to do cosine. If you take the average, not the average power, but average value, let's say, average amplitude? No, average. So when you just do integration of cosine, it's going to be 0, right? Because cosine always go positive, negative, positive, negative. The mean is 0. But when you do the power, if you want to get the average power, power is going to be square. So what you need to do is cosine square and take an integration. So what's going to be the value? Integration of cosine square. What is the value? 1 over 2. Just 1 over 2. Why is that? Simply because cosine square is 1 over 2, 1 plus cosine 2x. Right? We always do that, right? And cosine 2x is another cosine with a different frequency. Frequency is double, but still it's a cosine. So integration of cosine is going to be 0. That's what I said, right? When you do the integration of cosine, it's going to be 0 anyway. So the integration of cosine 2x, again 0. Integration of cosine 5x, again 0. Cosine is just 0, right? Integration of cosine 0. So half 1 plus cosine 2x, cosine 2x will be 0 when you do integration. But 1 over 2 is a constant. So you just get 1 over 2. Right? Yeah, so integration of cosine square is going to be 1 over 2, simply. So therefore, when you have this one as st, and let's take a look at the average power, then what you need to do is a square of this, and in doing integration. Then what do you get? You're going to get from here, from cosine, you're going to get 1 over 2, and you're going to get, this is a coefficient, right? You're going to get a square of this. So you're going to get this one. Okay? So that's going to be your average power. You see this one is a square, Bessel function of square root of Bessel function. You're going to have 1 over 2, right? Because we have a cosine, and cosine squared is a 1 over 2. So you multiply 1 over 2, and this is function. So that's going to be simply average power of the ST we are transmitting. Okay? So that's what they mean. You need to know how to calculate the average power. Okay? Simply, that's going to be integration and square of your function. Okay? That's going to be your average power, simply. Okay, now let's take a look at what it looks like in the frequency domain in this picture. What this picture shows you is that we basically try a different beta value. Beta equal to 1. The second figure shows beta equal to 2. This is a beta equal to 5. So now we have a different beta value. But let's go back to our beta definition. Our beta is this one. Delta F divided by Fm. So now we have a different value of beta. Let's say beta equal to 1 and beta equal to 2. Then there are two ways to change it. Right? Maybe if you want to double the beta value, you can make a Fm constant and double the delta F. That's one way. Right? So you make this Fm constant and you make a double of this delta F. Then beta is again double. Or another way is delta F is constant, and this Fm is now become half. Okay, half of that, half of the previous value. Then beta is again double. Right? We have two different ways. So given that this figure shows you that our Fm is constant, how do you know? You compare these three figures. Now you see the gap, right? Gap between the arrows. That's Fm. Why? Because the middle one is always what? Fc. Fc frequency. This is a frequency domain. So middle one is always carrier component, Fc. And the next one, Fc plus Fm. Fc plus 2Fm. Something like this, right? Same thing for here. Same thing for second figure. The middle one is always Fc. Next one is Fc plus Fm. So the gap between the two different arrows, two different impulse response, impulse function, this gap is Fm. And you see that this gap and this gap all the same, right? Which means that Fm is constant. This Fm is fixed. If the Fm is fixed, how do you change the beta? How to change it is your delta F becomes changed, right? Because the beta is delta F divided by Fm. That's the definition, right? Yeah, so that's the definition. So in order to change the beta, you need to change the delta f because Fm is constant, right? So that's what you can see here. Here, when beta equal to 1, you see that this is a 2 delta f, and when beta equal to 2, now you see a little bit bigger delta f. Here, in case of beta equal to 5, you have even bigger delta f. So that's what happened when you change the beta value. So this is one way. Go to the next slide. This one is actually pretty much the same thing, but this one also, the first picture is a beta equal to 1, beta equal to 2, beta equal to 5. But in this case, we are going to fix the delta f. Delta f is constant. Okay, if the delta f is constant, but we want to change the beta value, what you need to do is Fm has to be changed. Right? So in this case, you see the Fm, right? This much of, this is always, the middle one is always Fc. The next one is Fc plus Fm, right? So this much is Fm. And you see that this Fm is different from this Fm, this Fm. Okay? You see the different Fm value, right? Because we have a different beta value. But delta F is fixed. So that's what you can see. In this case, the delta F is fixed. So you see the delta F is the same. So all delta F is same. So from these two, from this figure and also the previous figure, what you can see is that when you have a high value of delta, large value of delta, okay, when you have a large value of delta, that's called wide band, right? What was the narrow band? In our previous narrow band, what happened was beta was small. Remember? Beta was a small value. So if the beta is small, like this, I mean, this is a large value of beta, but this is a relatively, this is small value. In this small value, now you see that within this delta value, you have only small number of impulse, right? In this case, only 3. However, if you increase the beta, now you have a lot of this impulse response within this beta, within this delta f. That's what you can see here. You can see the same thing in the previous slide. When you look at this previous slide, right? In this case, delta f, Fm is constant, but delta f changes. But still, you can see the same observation here. When beta is equal to small, we have only this small beta, small delta f. So you only have a 3 frequency component. But if you increase the beta into 5, now you have a big delta f. So you see a bunch of impulse functions, impulse frequency components inside this delta f, right? So you can see the same observation from both of them. So this Carson's rule, there's a rule called the Carson's rule. And in this Carson's rule, in theory, tells you, what is the bandwidth of the FM signal. Okay, that's the Carson's rule. So in general, as we said earlier, in FM signal, you have infinite number of side frequencies, right? You have infinite number of side frequencies. But in practical systems, you cannot have infinite. You cannot have infinite frequencies. So therefore, what you need to do is you have to limit your bandwidth. And some other frequencies out of your band, you have to remove it, right? You have to limit your bandwidth. So what would be the best bandwidth? Because you have to fix it. You have to limit. So how do you decide? How do you decide the bandwidth? So Carson's rule tells you how much is the bandwidth. Okay? That's why we use this one. So it says that in theory, the FM has the infinite number of side frequencies, but in practice, in practical systems, in actual systems, FM wave is effectively limited to a certain finite number, not infinite, finite number of a frequency, of side frequencies. So what we need to decide is how many frequencies we are going to keep and how many we're going to remove it. We need to decide that, right? So simply speaking, you can look at the last equation here. So this last equation is Carson's rule. So Carson's rule simply tells you that if you decide the bandwidth Bt in this way, okay, in this way, then you can decide, how many frequency component you want to keep and how many remove. So this one simply is a 2 delta f plus 2 fm. So that's the Carson's rule. But this equation is only true for singleton message. Okay, we are still talking about singleton message. So our message is a single tone. Our message has only FM frequencies. Okay. Yeah. So that's what it means. So simply speaking, right? Our message is a single tone. So our message has only one frequency. But when you do this FM modulation, what happens is the output of the FM modulation, you have an infinite number of frequencies. Your original message has a single frequency. But when you do the FM, you have an infinite number of frequencies. That's a problem, right? But you cannot transmit infinite frequencies. So somehow you need to decide how many frequencies you're going to keep it and how many you need to remove it. So this Carson's rule tells you you want to keep this much of bandwidth. Okay? So look at here. So 2 delta f plus 2 fm. So this is the bandwidth you want to have. So if you have some frequency component within that bandwidth, you want to keep it. All the other things, just remove it. That's what that means. Right? So Carson's rule helps you how to decide the bandwidth. What if we have some general signal? So in the previous signal, it's still for singleton message. But if your message is not single tone, okay, then we're going to look at that in the next slide. But yeah, let's move on to this one. Maybe that's a little bit easier to understand. Here, then how do you decide? Look at this equation. What this means is, what was the Bessel function? The Bessel function was the amplitude of each frequency component, right? That was the coefficient of each frequency. And now how to decide is, you're going to keep only the frequency component with the higher than 1% of your original signal. So here's what that means. You have your original signal has a certain energy. Okay, certain energy. Now this energy, your original energy, when you go to the FM modulation, it becomes like infinite signal, infinite frequencies. Right? Infinite frequencies. Now what we need to decide is we have to remove some of them. What that means is you're going to lose some of the energy because you remove some of them. So whatever energy you have in that frequency, you're going to remove it. But what we want to do is we're going to lose only less than 1% of energy. We're going to still keep 99% of the energy. That's what we want. So you don't want to remove the big frequency component, right? You want to remove only the small ones. So how do you decide? The threshold is 1%. That's what they mean. So you want to keep it. You want to keep some frequency if that frequency is higher than 1%. Put it in other words, if you see certain frequency component, but that frequency component has a very small amplitude, like less than 1%, you can remove it. That's what that means. Okay, so that's what they mean. So this table and this figure shows that when you change the modulation index beta, let's say beta is a 0.1. That's a very small beta value. And you increase it up to 30. Then what is the number of significant side frequencies in your bandwidth? If your beta is a small value, then you have only 2. That was the case of narrowband. Remember in narrowband we have FC, and we also have FC plus FM, FC minus FM. So we have only 2 side frequencies. That's the case. Okay, 2 side frequencies. 2. But when you increase the beta, we have more side frequencies in our bandwidth. That's what we already looked at in this figure, right? So when you have a high beta value, within our bandwidth, we have a more number of side frequencies, right? We have a more and more side frequencies within our bandwidth when you have a large number of beta. So that's what it means. When you increase the beta value, let's say beta equal to 5, in that case, within our bandwidth, we have 16 different side frequencies. That's what it means. If you increase it even more, you have even more side frequencies within our bandwidth. But in this case, in this figure, what we want to see is we want to look at the normalized bandwidth. What that means is beta BT divided by delta F, this one. Our bandwidth divided by delta F. So what that means is, let's go back to Carson's rule here. This is a Carson's rule. So this is a beta T, our bandwidth. And bandwidth, based on the Carson's rule, beta, the bandwidth equals to 2 delta F plus 2 FM. So now let's divide the whole thing, divide by delta F. Okay? Then what that means is BT divided by delta F, then it's going to be 2 plus 2 times FM divided by delta F, right? So it's like 2 plus something. Okay? 2 plus 2 FM divided by delta F, right? So that's this one. So what that means is if you increase the beta value, modulation index beta, now this normalized bandwidth is approaching to 2. Meaning that in Carson's rule, we have already 2 plus some other value, but this value is decreasing when you have large beta. You can see it here actually. If you increase the beta value here, right? This one and this one is same. Why is that? Because beta, what's the definition of beta? Beta is delta F divided by FM. So you can put that together. This one and this one is same. So if you increase the beta, now the 1 over beta becomes small. It becomes small and small. So therefore, eventually, this becomes 0, right? Eventually. Then it's going to be like a beta T, our bandwidth becomes 2 delta F. Eventually, if you increase the beta a lot, right? That's what it means. But what we can see in this figure is BT divided by delta F. So eventually, it will approach to 2. So simply speaking, what that means is, this is the case of beta equal to 1. This is the case of beta equal to 5. Now this is a 2 delta F, and BT is our bandwidth. And based on the Carson's rule, your the bandwidth equals to 2 delta F plus 2 FM, right? So it's like this is a 2 delta F, and this is 1 delta F, another delta F. So 2 delta F, FM, this is another FM. So 2 delta F plus 2 FM, that's going to be this much. So that's a BT. So let's compare this 2 delta F and BT. BT relatively is much bigger than 2 delta F. Same thing for this one. This much is 2 delta F, and BT is only that much. So compare these two, looks almost similar, right? So if you increase the beta, now it's a 5, but let's increase the beta to, let's say, 20. Then 2 delta F and BT is almost the same, right? What that means is this one approaches to 2. Okay, that's the same thing. So that's a normalized bandwidth. That's what they mean, right? BT divided by delta F, that's a normalized bandwidth. Given the delta F, how much is your bandwidth? That's a normalized bandwidth. Same here. Given the delta F, what is your actual bandwidth? You need to use this much bandwidth. Then you see that this normalized bandwidth, BT divided by delta F, this one is almost close to 2. This one much higher than 2, right? This slide just tells you that if our message is not single tone, but if our message has a multiple frequency, then you can change the previous Carson's rule into this way. The previous Carson's rule said that when your message has only single tone, FM, then it's going to be 2 delta F plus 2 FM. But now in this case, our message is not single tone. Your message has its own bandwidth because your message now has multiple frequencies. So your message has a bandwidth, D, in that W. In that case, put that bandwidth here instead of FM. Then you're going to get this one. So this one almost same as Carson's rule. Only difference is that in the previous Carson's rule, we were talking about single tone message. So this one was FM. Now it's not single tone message. In this case, your message has a bandwidth W. So we just replace FM with a W. So same thing. Okay, that was the basic theory of FM. And what we see from the next couple of slides is then how can you generate the FM signal? So first way, direct method, and second is indirect method. And direct method means that let's say you have a message, maybe a sinusoidal message. Then based on the sinusoidal message, you put this message into frequency. That's a direct method. What that means is how do you change the frequency? Your message should go to, in general, how do you change the frequency? How do you make the frequency? Original frequency. I mean, mixer is the hardware device to mix the two different frequencies. But where does the original frequency come from? Oscillator, right? So in order to do FM, your message should go to the oscillator, right? But that's not easy. But this direct method is that kind of way. So your message should go to the oscillator circuit and then change the frequency. So that's a direct method. But this one actually does not really make sense in hardware. Okay, we are not doing this much. In theory, this one makes sense. We understood it that way, right? We keep saying that message go to the frequency. In that case, in hardware, message really need to go to the oscillator because the oscillator makes the frequency, right? Message should go to oscillator, but that's difficult, really. So what we typically do is the second method, indirect method. In this indirect method, let's go to the next slide. This is how to do it. You have your original message empty. From this message empty, first thing is to do the integration, and then you multiply, you put that into the cosine carrier. Then what do you get? Here is a narrowband FM. This one actually is a narrowband FM. Here, narrowband FM modulator. So we are going to get narrowband FM. Once you get the narrowband FM, now we put this narrowband FM signal into the frequency multiplier in order to get wideband FM. So first we generate the narrowband FM signal, put that into the frequency multiplier, then you're going to get wideband FM. So now we learned the frequency, narrowband FM signal before, and now we know what this looks like, but we don't know what it is, frequency multiplier. So let's look at the frequency multiplier. Simply speaking, the frequency multiplier is a nonlinear device. Okay, nonlinear device. Why do we need a nonlinear device? Simply, nonlinear means this is not linear, right? So for example, let's say this is the input-output relationship of that device. If the input-output relationship of a device is like this, let's say we don't have this. We only have this one. So output equals to A times ST. In this case, this is a linear, right? Because it's like Y equal to AX, right? So this is a linear relationship. This is input, and multiply some value or gain, you get output. So that's a linear relationship. But in our device, we have a multiple square, cube, and all the other components. So that's a nonlinear. So think about the polynomial equation. This is like a quadratic equation. We have even s times s to the power n. So this is like a nonlinear curve, right? This is not a linear curve. So this is the device. This is the input-output relationship. So why do we need this? Simply, let's think about only this one. It's still nonlinear because we have a square term. So forget all these things and think about only square. Think about only y equal to ax plus b. I think this is wrong. This is 2, right? A times 2, a sub 2. So it's like y equal to ax plus bs squared. Something like this, right? Still, this is a quadratic function, so this is not linear. Still nonlinear. So in this case, now let's use our input as a cosine. We always use a cosine as input, right? Some simple input. Let's put the cosine signal into this device. Okay, input is st, but our input is a cosine. Okay, let's put the cosine into this one and let's see what do you get as output. What do you get? What is the output when you use that cosine as the input in this device? Let's look at this one first. Linear, simple way. Let's say our input is a cosine. So when st is a cosine, what is the output? Same cosine. Just multiply gain. Just maybe the bigger or smaller, depending on a, but still the same cosine. Now we have a nonlinear device like this, and our st, our input is a cosine. So what do you get? What do you get at the output? It's like a cosine plus b cosine square, right? What is a cosine square? It's a 1 over 2, 1 plus cosine 2 times frequency, right? Let's say this is a cosine fc, then we have a cosine 2fc. So the output you have is, our input was only the fc frequency, but the output, we have fc frequency, we also have a 2fc. Because we have a square generate the 2fc frequency, right? So the output, in this case, is going to be fc frequency and also 2fc frequency and also dc. So we have that kind of frequency here, right? Now let's think about another term, c s3, s cube term. Then what do you get as output? It's like a cosine fc frequency, 2fc, 3fc, because we have a cube term, right? S to the power 3. So from that, we are going to get the 3 times frequency, right? 3fc, right? So if we have n terms, s squared, s cubed, and all the way to s to the power n, now we are going to get all this frequency, like fm, like let's say our input is fm, frequency fm, cosine fm, then we're going to get fm frequency, 2fm, 3fm, 4fm, all this fm, right? And n times fm eventually. So you're going to get all these frequencies because this device has this input-output relationship. We're going to once you put the fm input, we're going to get bunch of frequency as output. Okay, so that's what happened in this device. So that's how you make these bunch of frequencies. These bunch of frequencies. See the output? So this is a new FM wave. That's the output. In this output, you see that you have a bunch of different frequency components. So that's how you make it. Because in frequency modulation, as we discussed earlier, even though you have a single tone as an input, your output you have infinite terms of frequency, right? So how do you make it? This is one way. You make a bunch of different frequency components by doing this one. Okay, so this is a block diagram. Yeah, so this is some general overview of FM signal. Okay, and we're going to continue a little bit more about FM next time. So we just talked about how to generate FM, right? So this is generation means transmission side, right? You generate FM signal at the transmitter, right? And we need to talk about how to receive, right? We didn't talk about receiver yet. So next time we're going to talk about the receiver side.